Hi there. Thanks for joining us. This is Space Nuts. My name is Andrew Dunkley, your host, and glad you could join us once again. Coming up on today's program, we are going to be looking literally at the oldest black hole yet seen. It's not only the oldest, it is big, in fact huge, and it's very, very hungry. We'll also be looking at an asteroid impact on Earth. Yes, it happened. Why are we still here? Fred will explain. And the Mars Copter has run into some communications issues. We'll cover all that, plus audience questions and a bit of homework coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us to hash out all of that and much, much more is Professor Fred Watson, Astronomer-at-Large. Hello, Fred.
What a surprise to see you there.
Yes. I was expecting someone else, but it was you. So I'm very happy about that.
Yeah, just as well, isn't it, really? Nobody else would put up would put up with our respective terrible banter. Anyway, I'm here and I'm glad you're there and all is well. It's going to be a hot day for you, I think, out there out west. It's hot here in Sydney.
Oh, yeah. Yeah, we're getting some really big numbers at the moment. 39 today, 40 tomorrow, 40 for Australia Day Friday. And then we might get a brief respite into the weekend proper, but yes, stinking hot. I imagine it's also going to be very windy on Australia Day, so I imagine we'll have fire weather warnings and all sorts of stuff. Dogs and cats living together. Oh, God, that's my favourite line. But yeah, it's all a bit hellish around here at the moment. I think I'd be better off pitching a tent on the sun at this point in time.
Yeah, maybe.
Yeah. Western summer, it's getting back to a normal Western summer. The last couple have been quite mild. So this one, like last summer, we only had one day over 40 degrees. And this season we've had, I think this is probably the 6th or 7th. So it's been very hot summer. Now, let's get down to business. The James Webb Space Telescope's been at it again, Fred, and this time it spied the oldest black hole yet seen, and it is a monster, and it is committing astronomical suicide by destroying its own galaxy by the sound of it. It's a very interesting story.
Galacticide, I guess it would be, wouldn't it? Because patricide is where you kill your dad. Galacticide. Yeah, that's, I think we've just invented something there. True. It is a good word. Yeah, I'll just write it down so I don't forget it.
Yeah, do that.
There you go. Galacticide in galaxy. Remember where you heard it first, folks. So observations led by from a team of international astronomers led by scientists at the University of Cambridge in the UK, and they used the James Webb Telescope to look at some very early galaxies, and by that I mean with a very long look-back time. So you're looking back to not very long after the birth of the universe. And we're talking now about a time probably about 400 million years after the Big Bang. So the Big Bang's currently estimated to be 13.8 billion years ago. So this goes back 13.4 billion years, these observations. And yes, what has been discovered is a massive, in fact, a supermassive black hole at the center of this galaxy. And by that, I don't think they've got a particularly precise number for it yet because it's so far away, but it is a few million times the mass of the sun. And that puts it very much in the supermassive region. And basically, what it does is throws another upset into our understanding of how galaxies and black holes form and grow. And so just to recap, black holes seem to come in two sorts. The stellar mass black holes, the mass typically of a star, a large star, but maybe 20 times the mass of the sun, and supermassive black holes, which are millions to billions of times the mass of the sun, with very little in between. The intermediate mass black holes which are thought to exist, and in fact, some might be lurking in the insides of what we call globular clusters of stars, but they're still very much more elusive than either the stellar mass black holes or the supermassive black holes. So how do supermassive black holes get so big? The thinking has always been that they start off with stellar mass size, modest sized black holes, just a few, maybe tens or even hundreds of times the mass of the sun. And they grow over time by accreting other materials. So if you've got one in the center of a youthful galaxy, there's a lot of gas in there. That gas can be sucked in to the black hole. That's the accretion process, and causes its mass to increase. But the problem is that is thought to be a process that takes billions of years. So you start off with something small and it grows to a supermassive black hole over a period of, as I said, billions of years. And this is only 400 million years after the Big Bang. And so, it's essentially thrown the cat among the pigeons. It's saying, well, how can we get a black hole this size so early in the universe? And the two ways that are being postulated are, first of all, maybe black holes, supermassive black holes, form in other ways. Excuse me, they might come into being as a supermassive black hole rather than come into being as a stellar mass black hole and then grow. Or they can gobble up material, the surroundings. In other words, they can accrete, to use the technical term, much more rapidly than was thought to be the case. And they're estimating it would have to be about 5 times the rate of gobbling up that we've been, that astronomers have been working with so far, a number that comes from studies of how we think black holes accrete material and grow. So that's the current state. We've got this conundrum, a black hole that should have taken more than 1 billion years to grow to the size that it has, but it's done it in 400 million years. And so it is a puzzle.
Well, yeah, and in doing what it's doing, it's also destroying everything around it. But it seems to be doing it in an unusual way. There's this a reference to an ultra-fast wind that's been caused by this process, and that's what's destroying the galaxy.
Yeah. Rather
than it eating the galaxy, it's actually destroying its, for want of a better term, food source. Yeah. That just sounds really bizarre.
Doesn't it? And so the wind itself, I mean, normally things that come out of black holes, and they don't come out of the black hole itself, they come out of the accretion disk. Normally the pattern is that you've got a black hole, it builds a kind of disk of material around it, which is gradually swirling into the black hole, and that's how it's gobbling up. And some of that material doesn't go into the black hole. It's diverted by magnetic fields into what we call polar jets that come out at right angles to the disk. And that's the wind. But it looks as though there's something else going on here. I don't know too much about this type of wind, because I would have expected, if you've got something that's really gobbling up material around it very quickly, the wind will be directed perpendicular to that disk. But it may well be that under some conditions you get a wind that's sort of blowing everywhere, what we would call isotropic in all directions. So yeah, it is as you said, that is maybe pushing away the gas that this black hole needs to keep on growing. And eventually that would stop the black hole from accreting. The black hole wouldn't go away. It would still be there, but it wouldn't be gobbling up material anymore. It would become what we call a quiescent black hole, which is a bit like the one at the center of our own galaxy. So really interesting stuff. One of the lead authors says this is the most exciting time in his career. It's a new era. The giant leap in sensitivity, especially in the infrared, is like upgrading from Galileo's telescope to a modern telescope overnight. Before Webb came online, I thought maybe the universe isn't so interesting when you go beyond what we could see with the Hubble Space Telescope. But that hasn't been the case at all. The universe has been quite generous in what it's showing us, and this is just the beginning. It's almost poetic, isn't it?
Very poetic. And it also that points out the fact that the James Webb Space Telescope has, as promised, delivered it. A lot of the time they say, this is the next big thing, it's going to do, yay. And then it goes up and you go, oh, it's a blob out of focus. But this one's actually delivering, and it's delivering spectacular results.
Very much so. And the hope is that the telescope will be able to probe even further back in time to look at even earlier black holes, and that might give some clues as to what's going on in the early history of black holes. If we start finding dozens of these supermassive black holes at a very early stage of the universe, I think it means we've got to do some really serious rethinking of what's going on in those early galaxies.
Yes, indeed. And this one's certainly thrown everybody in a spin because of A, how old it is, B, how big it is, and C, what it's actually doing to its neighbourhood and how it's doing that. It's all very, it's sort of thrown the baby out with the bathwater in terms of theory in some respects, I suppose. So we find these things and it opens up so many more questions, but they will hopefully ultimately lead to answers. That's the hope, isn't it, Brett?
That's the way science works. Yes, that's right. So we've got observations which don't fit the theory that exists. So you rebuild the theory and then do more observations to see whether the theory is upheld. It's very much the way astronomy works, even at these great distances from our own present time, great distances in time.
All right. If you want to chase up that story about this incredible discovery and this rather strange black hole, phys.org, phys.org is the website where you can find that article. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, Fred, let's move on to something that happened more recently than that black hole forming. In fact, this happened only a few days ago. Earth was hit by an asteroid. It has been reported in the popular press, and we're still here to talk about it. Now, what I understand is this one wasn't as big as the one that killed off the dinosaurs, but I have heard a report that there was a small lizard with a limp after this one.
Not sure that they...
They
don't have too many lizards out and about in January in eastern Germany because the temperature is pretty low.
Never let the truth get in the way of a good joke, though, Fred.
Quite so. So an object that was actually well recorded by security cameras and dash cams and all the rest of it. An object that came to Earth over Berlin, in fact, in the eastern half of Germany, over the weekend, Sunday morning, their time. So lots of video and a lot of people really interested in it. It's got a name, as all good asteroids do. So it's obviously being counted as an asteroid, even though it was a small object. Its name is 2024 BX1. And you might remember that the way those numbers work is the date or the year, 2024. The B says it was the second half of January when it was discovered, because it's alphabetical for each half month throughout the year. It's very cleverly done. And then the alphabetical order and then a number after that. So it's landed outside Berlin. The interesting bit is that it was an astronomer in Hungary, and I don't know whether this gentleman, Christian Sarnesky, I think is how we would anglicize his name. I don't know whether he's an amateur astronomer or a professional, but he discovered it and alerted the International Astronomical Union via there's an asteroid discovery system that you can use, and that was then confirmed by NASA, presumably with one of those telescopes, and this all happened kind of 20 minutes before the impact. I think the discovery was made several hours before impact. NASA confirmed it 20 minutes before impact. with an absolutely spot-on prediction of where it would land or where it would disintegrate over, and at what time, and it was all right on the money. So this is interesting because it's the 8th time that an asteroid has been discovered before it hits the Earth. And that's telling you that the systems are working, particularly because this is thought to be about 1 meter across. So it's what you would call a very small asteroid and maybe a large meteoroid. That's a sort of grey area between the two. So yeah, it's very, very satisfactory outcome of what we're hoping to do in the world of planetary protection, as it's called. This idea of trying to monitor threats posed by asteroids before they happen. The other thing is that the gentleman who I mentioned, Christian Sarnesky, forgive me if I'm mispronouncing his name, has discovered 3 that have been hitting the Earth. In other words, first he's done 3 of these 8 asteroids that have been discovered before they hit the Earth. Very well-known asteroid hunter.
Yes, and seems to be very good at what he does. Yeah. Now, this one, as you said, around about 1 meter, which is a little bit smaller than the one that hit the Earth and brought about the beginning of the end of the dinosaurs. That one was as big as Mount Everest or something, wasn't it? And this one broke up on impact, but they do think that it would have showered parts of Europe with micro meteorites. I think they referred to the mass.
So lots of small bits of debris, and it's possible that some of them might be recovered. It's it's wintertime up there. Meteorites are generally black, and often they're discovered in Antarctica, where they're against a white background because of snow. Maybe they will be discovered perhaps in the regions of Eastern Europe, where this object is thought to have fallen, or bits of this object are thought to have fallen.
So if you do want to, if you're a listener from that part of the world and you want to go out and hunt for these micrometeorites, just keep an eye out for limping lizards, and
yeah.
you might
I
get
think
lucky.
yes. I think you'd probably be luckier to find a lizard than you would a meteorite at this time of year, because the lizards would be well hibernated.
I imagine so. They would, but so when you hear the word asteroid, you automatically think about the dinosaurs and the humongous rocks that have hit Earth in the past, and you make that assumption. So when you hear that we've actually been hit by an asteroid, you go, "Oh no!" But they're not always monsters,
no,
are
they're
they?
Not. In fact, that's the interesting part about it. At the moment, all these telescopes that are looking for asteroids are concentrating on the small ones, because the big ones, most of them have already been found, which is good news.
Yeah. Yeah, we've actually got to watch out for the ones that are just a bit big enough just to get through. They're the ones to.
I think did we talk about that last week? I was talking about the asteroid protection group that I was sitting with in Vienna. Yeah, they postulated a scenario in which, exactly as you said, a 1 kilometer asteroid could get through. It has to be in a very unusual orbit, but it's possible.
Yeah, never say never.
Exactly.
But we've done the double asteroid redirection test, and we know it works. So,
exactly.
We live in hope.
You had your T-shirt on last week, didn't you, with the double asteroid redirection test? Yes, that's right.
It did. Now, let's move on to Mars, and the Mars Copter has made the news, and that's because it stopped working. In fact, I think it was in the middle of a flight when it lost comms with NASA, and they thought, end of mission. So, yeah, it got a bit scary there for a while, but then it suddenly went, no, sorry, nothing to see here. It's all good. I'm here. So what do we know about this?
So exactly as you've said, so it's not the first time. Let's just preface it. It's not the first time that the Copter has suffered communications issues, and I think the longest was uh, 2 months or something that it was out of contact.
63 days.
2 months. But this was something different from that. And what they were doing was doing a test flight. This is last week. And it was, wait for this number blows me away, Andrew. It was Ingenuity's 72nd liftoff off the planet Mars, when it was originally planned to have 5 flights. So 72 is just an astonishing number, and it's been so invaluable to the Perseverance mission. So that's fantastic stuff. Anyway, it was a quick test that they were doing. I think it was basically just an up and down. In fact, they describe it as a quick pop-up vertical flight to check out the helicopter systems following an unplanned early landing during its previous flight. So there was an issue with the previous flight, and then they did this up and down, but as it was coming down, it lost communications again before touchdown. Now, the great thing is this helicopter is equipped with basically autonomous systems, and it has to be because the delay, the time delay between a signal leaving Earth, getting to Mars, and then coming back again is far too long to control a helicopter with. So it's got its own brain and it does its own decisions, and apparently landed safely, although it's out of sight of Perseverance itself. They can't actually see it. So there is talk, or there was talk, of Perseverance actually having a quick drive over to have a look at it, a visual inspection, just to see if it's okay. But at least it's talking to Perseverance, so they've got communications restored, and apparently there was a post on X, formerly Twitter, asking if Ingenuity would fly again, and JPL, Jet Propulsion Laboratory, who run the whole show, said that they are going to be assessing the new information that's come from that before they'll decide whether it'll fly again. So that may have been its last flight, Andrew. On the other hand, it may just...
That would be sad.
It would be sad.
That would be very sad.
And it's just done such an extraordinary job of reconnaissance in the area around Perseverance. It's apparently covered 17 kilometres and gone up to 24 metres, which is quite a height for a little baby helicopter like that. And I think the other thing...
Yeah, it's only a tiny...
That's right, 1.8 kilograms. Its rotors, if I remember rightly, are 1.2 metres long, 2 of them rotating in opposite directions so that they balance out the torque. The thing that gets me, though, is, Martian nights, the temperature goes way down, probably the minus 60s and things like that. And in fact, the average temperature on Mars is minus 63, I think, if I remember rightly. Somebody might correct me if I've got it wrong, just remembering. But Martian nights are very, very cold, and it's the solar panels, which sit on top of the rotors, are absolutely vital for keeping it warm by the electric current that they generate for its batteries during the day, which then keep the little spacecraft warm. Not really a spacecraft, it's an aircraft, isn't it? They keep it warm during the night.
Yeah, it's been one of the great success stories of NASA for it to have lasted a heck of a lot longer than they planned, 72 missions versus the planned 5, but also to survive the hostile conditions for such a long time. That's amazing.
Yes, an extraordinary success story. And we're full of admiration for the engineers who invented it and built it, basically.
Yeah, and hopefully not the last we'll see of it, but if it is, it's still been a resounding success. You mentioned X, formerly known as Twitter. Did you hear that? I've forgotten the name of it. YouTube, Twitter, and Facebook are going to merge. Did you hear about this?
I didn't.
It's going to be called. Yeah, it's going to be called You Twitface.
I should have seen that one coming, shouldn't I?
Probably, yeah. Oh boy! Listen, I was going to save this till later, but I think we will tackle it now. It's a bit of homework. Last week, we were talking about a dark energy survey where it brought into question our understanding of the cosmological constant. Now, we've had a question from Lindsay asking us to explain the equation of state, the value of the cosmological constant, which is minus 0.1. But this survey has rejigged that number to be minus 0.08. But what we didn't do, and I probably should have asked the question at the time, is what is that? How do they work that out? What is the equation of state?
It comes from physics, really, Andrew, as you might not be surprised. And it comes from considerations of a perfect fluid, which has its own definition. So if you imagine the universe as a perfect fluid, you can characterize it by this number, which is the equation of state. It's equal to the ratio of its pressure to its energy density. And it's sort of, it's part and parcel of thermodynamics. So the pressure to the energy density ratio doesn't really feed much into our understanding of what's happening in the far universe. But in the case that we're talking about, which is the cosmological equation of state, the equation of state as the universe as a whole, and how it relates to the accelerated expansion of the universe, it actually kind of makes more sense. I'm going to just try and read a little bit about the equation of state from the good old Wikipedia website. The accelerated expansion of the universe can be characterized by the equation of state of dark energy. So it's the dark energy itself whose equation of state you're looking at. In the simplest case, the equation of state of the cosmological constant, that's what we were talking about last week, is -1. In this case, I won't go into more detail, but if you've got an acceleration of an equation of state which is less than -1/3, then you've got a different status, and I think you've got basically something that changes with time. That's the bottom line of it all. I'm not explaining this very well at all, Andrew, and I hope there aren't any cosmologists listening, or else they'll be turning in their, well, not in their graves, but they're turning in their beds. So there is another hypothetical thing that comes into it as well, which is phantom energy. That's a term I'm not familiar with. Phantom energy is, it's as I said, a hypothetical form of energy, which actually has a different characteristic in the equation of state. In other words, it's less than -1. It basically, it's a lot of quite deep physics, which is, as you're no doubt noticing, not that easy to put into simple words.
No, I can imagine. Well, I just heard it. But the bottom line is, the bottom line is, the dark energy survey we talked about last week has put a question mark over the equation of state of the cosmological constant.
Thank you very much.
Okay.
I'm glad you're here, Andrew.
That's
you can.
That's the simple explanation, and there's only a 5% chance that the -0.1 is still relevant.
Yeah, it's actually it's minus. It's -1. I'm not sure. You might be looking at something slightly different, but it is -1 that it's thought to be, and I think the value was rather smaller, wasn't it? -0.8 or something like that was coming out of the dark energy survey.
Yeah, something like that. Yep. Yes, you're right. Yeah, and I'm just looking at the article now. -1, and now it's looking like it's -0.8. So yes, My apologies. But yeah, thanks for the question, Lindsay. Nice to be able to follow that up and get let's call it an explanation. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, Fred, let's see if we can answer some questions on other matters. And the first one, forgive me if I've messed your name up because I just couldn't quite catch it in the dialogue. In fact, I won't even say your name because you're going to say it for us.
Hello, Fred and Andrew. Thank you for a great podcast. My name is Manne Sjöberg and I live in Sweden. And I sent the question about why is astronomy important? Thank you for that answer. I've been thinking. A lot of celestial objects rotates, spins, like our planet, our solar system, the stars, the galaxies, and even black holes, if I understand it correctly. My question is, does the universe rotate? And is it possible that we have misinterpreted the expansion of the universe, but in reality it just spins and we are moving away from objects, like the moon is escaping Earth? Thank you again, and hej då.
Thank you, Mon, I think he said, but I'm sorry if I got that wrong. Does the universe rotate? The whole universe?
Apparently not. And, the question that you immediately ask, Andrew, is how would we know?
Well, that was the next question.
How do you know if it's rotating or not? Because you're in it, and the universe, by definition, is everything that we can observe or understand, detect. So it's basically one of these questions, though, that people do ask in exactly the way that we've just heard today. That is because it's a natural thing to ask, that everything in the universe seems to rotate, absolutely everything. But is the universe itself rotating? And I guess the best way to put it is that there is no evidence that the universe is rotating by any means that we investigate. Whatever means we use to investigate it, there's no evidence that we do find a rotating universe. So the bottom line is the fact that we're sitting in the universe itself, and the only things that we can measure, certainly at cosmological distances, are the redshifts, the expansion of the universe, the way its shape is changing, if I can put it that way. Even though we don't know whether the universe has a shape, we can detect its expansion. So that is one of the things that we do know, that the universe is expanding. I have seen articles in the past that suggest. I haven't ever followed this up, so I don't know, what the details are. I should do that. Maybe a bit more homework. That suggests that if the universe was rotating, we'd be able to travel backwards in time. That seems a very unlikely scenario to me, because relativity doesn't like the idea of backward time travel. You can go forward, but not backwards. So it's one that might be worth following up. But no evidence that the universe is rotating.
Look, this is a really simple explanation on my part, but I could imagine if it was rotating, it'd be like a glass of water. When you've got a glass of water and you put something in the water and then you rotate the glass, it doesn't really affect what's inside. You know what I'm saying? So even if it was rotating, it might not do anything.
That's an interesting analogue, because it almost counteracts the argument, because if you were inside a glass of water and it was rotating, what you'd see would be the effect of the centrifugal force of the water being pushed outwards, and you might think you were in an expanding glass of water. And if you carry that to the universe, somebody's going to say, "Oh, it's expanding because it's rotating." But that implies there being a.
Well, that's what Mon was asking, though, because the second part of his question was, if the universe is rotating, does that change the expansion theory?
Yeah. So I missed that bit. I was too busy worrying about the rotation of the universe. It's thought not to be, and I guess one of the things that comes into this. Sorry, I'm floundering for words here. One of the points is that if we take the traditional definition of a universe, which is everything we can see or measure or detect, then we would have no way of knowing if it's rotating, because there's no frame of reference outside it within which it's rotating. So the answer would be no. And I think the only way that you could contemplate a rotating universe would be by accepting the premise that there are other universes out there, that ours is just one of many universes. Then if you take that step, then you might have the possibility that it's rotating. But as I said, there's no evidence that it is.
Okay. Yeah. Gee, it certainly dredges up all sorts of questions and ideas, and you'd need a very big water cooler to stand around and talk about this, I think. But a great question, though, and thanks for sending it in. Let's go to a text question. This one comes from Lachlan James in Minnesota. He says, hello from the great state of Minnesota. That's a coincidence, because that's where I thought it was from. Right off the bat, thank you so much for your educational insight and incredibly down-to-earth, pun intended, podcast. You make standing at the mill so much more enjoyable. I started at the very beginning of your show, and I'm currently in the middle of May 2021, so I've got a ways to go before I catch up. But my question is a bit of an abstract one. Suppose you discover an anomalous telescope of irrelevant size, and what makes this telescope anomalous is that when you look through it, it will show you whatever celestial body it's pointed at in real one-to-one time. What is the first thing you would look at, supposing there's nothing in the way? Both from a standpoint of personal choice and a broader standpoint of humanity as a whole, wanting to learn as much as we can about the universe. Very much looking forward to hearing your thoughts. Thanks, fellas. James in Minnesota. So you've got a telescope. You can look anywhere in the universe in real time. What do you look at, Fred? First and foremost.
I think we've discussed this before, actually, Andrew. And I'm trying to remember what I said then.
We do get questions like this.
I think it's a similar question to one we've had before. I mean, what I would really like to see, and it's not really aligned with this question particularly well, but if I could take a telescope anywhere and look, I would love to see our galaxy from the outside. So not only would I be wanting to see, this hypothetical telescope to see anything instantaneously without the delay of time, then not only would I want to do that, I'd want to move it as well, so I could see what the sweep of our galaxy would look like from the outside. So it's taking the question a little bit further than than James probably intended. And so maybe I'm answering it.
No, fair enough.
That's what I'd like to do. Take this hypothetical super duper telescope, plonk it something like 100,000 light years above the pole of our galaxy. It might be a dangerous place, actually, because the pole of our galaxy has occasionally been known to be the source of some high energy material coming from the super massive black hole at the middle of the galaxy. Could be a dangerous place, but it will give you a beautiful view down on the spiral structure of our galaxy, and that's what I'd love to see.
Okay. No, that's a good answer. I wouldn't have thought of that. For me, James, let's just stretch this as far as we possibly can. Literally, I would want to see the actual edge of the universe. I'd want to see what's going on beyond the visible universe. You said assuming nothing's in the way. Well, let's just move all that stuff out of the way. I would point the telescope, and I could go any direction I want, and just find the actual edge of the expanding universe to see what's going on. That's what I'd want to see, because that's one of the great mysteries. So for me, that's the answer. What do you reckon?
Well,
Fred?
we don't think it's got an edge. That's the trouble.
Yeah, I know. Well, let's assume it has.
So
I'd want to see what's going on out there.
Yeah.
At the expansion point, whatever it is. That's where my brain's at.
It is interesting because what we see when we look as far out as you are talking about there, we see the cosmic microwave background radiation, but that's because we're looking back in the past. And what James is saying is you're not looking back in the past, you're looking at what it is like now. And so it could be infinite. You might not run against an edge, Andrew. That's the conundrum of cosmology. No. We don't know whether the universe is infinite or not.
But that's why we want to have a look. That's why I want a loan of James's telescope.
You've given a very profound answer there, which I applaud. It's better than mine.
No, but it does. I love these. These what if questions that we get sent occasionally. They're good fun. Thanks, James. And our final question this week is from Ian.
Hello, this is Ian from Cambridge. Just got a simple question. What is the temperature of space around sort of the Earth orbit from the Sun? So the distance from the Earth to the Sun. What's the temperature of space? I asked the question because when I Google it, it says it's about 2.7 Kelvin. But then you hear the James Webb Telescope that one side is very, very hot and the other side of the shield is cold. So I don't understand how the general temperature of space from distance from Earth to the Sun is only 2 Kelvin. Appreciate it if you can let me know. Thank you very much.
Okay, we'll be sending you an email. Or we can ask Fred, what's the temperature of space? I think when he refers to one side of the James Webb being hot and the other side being cold, that's because of the radiation effect, isn't it, of the sun? Whereas in general space, which is what it is, nothing-ish, there's a temperature, I imagine, and that's what he's asking about in the vicinity of Earth.
The background temperature of space is indeed 2.7 degrees Kelvin. And what that is the radiation from the Big Bang. It's actually the temperature of the cosmic microwave background radiation. So when you look at, we just talked about it, you're looking back so far in time, you're seeing a time when the universe was still glowing brightly, it was still luminous. It's now visible in radio waves, microwaves, because of the expansion of the universe, stretching the visible light wavelength out to microwave wavelengths by a factor of about 1300, I think, if I remember rightly. So that's the underlying temperature of space, and it is indeed 2.7. We can generate, believe it or not, here on Earth, temperatures colder than that, much nearer to absolute zero than that 2.7 degrees. So on Earth, you can generate cold temperatures. But exactly as you've said, in the vicinity of a star like the Sun, you've got radiation coming from that object. It doesn't affect the temperature of space itself, but as soon as that radiation falls on another object, then it heats it up. It's exactly how infrared radiation works. So it is a higher temperature on the surface that you're measuring. But if you were out in the middle of nowhere in space and you had a thermometer 2.7 degrees, it would be what we call a bolometer, actually. A bolometer is a device that measures temperature across all wavelengths. So 2.7 degrees is the right answer. So Ian, your bafflement is understandable, but that's the correct answer.
I'm just stunned that I actually got one right.
You did.
So
You were right on the money. You don't need me. You could just have a go at the equation of state as well.
Yeah. I couldn't do this. Couldn't do this by myself. Yeah. Thank you, Ian. It's a great question, and it certainly cleared that up. And we appreciate your questions and your comments. And even if you want to send us corrections, we ignore them. But you can send them anyway via our website. Via our website, spacenutspodcast.com or spacenuts.io. We'd love to hear from you, whether it's in text or audio form. If you do send an audio question or even a text question, don't forget to tell us who you are or where you're from, like James in Minnesota, who's going to invent a new telescope. It's going to be called the James at Minnesota Space Telescope, and it will see everything in real time. That would be an absolute. You'd make a couple of dollars out of that, unless you sold it to the government. Then they'd make you pay to give it to them. But anyway, lovely to hear from all of you. And Fred, as always, thank you. That brings us to the very end of this episode.
And none too early. Thank you, Andrew. Good to talk, and we might speak again next time.
We might too. We might. Fred Watson, Astronomer-at-Large. As always, we thank him for his very precious time. And to Hugh in the studio, thank you too, for reasons I'll have to look up. And from me, Andrew Dunkley, good to have your company. Hope you can join us on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.